Welcome to our concluding agenda point for today. And as my colleague Lucas mentioned, it's a fireside chat on the subject, the common interplay of high-performance computing and quantum computing. So we continue the topic of integration between high performance and quantum computing, which we started today in the beginning of our program. And as my first guest, I will have today two guests, and as my first guest, I would like to invite Dr. Jan Goetz, whom we already introduced in the beginning of the program, and he's a co-founder and a CEO of IQM Quantum Computers. Welcome, Jan, nice to see you again.
Hello, thanks for having me again. It's a pleasure.
I would like to start with asking you the following question. IQM Quantum Computers is an example of a successful company, a successful startup in the area of quantum computing. And you already addressed this topic a little bit in your presentation. Can you please tell a bit about the history of this startup first, like how it was born and what was your motivation? How did you came to the idea to start a company in the area of quantum computing despite that technology is still being relatively immature and there's a lot of uncertainty connected to it?
Yeah, sure. Happy to share a little bit the history of the company. So it's now around 3 years ago, actually, that we started with these ideas. And as many startups in the field of quantum, it's a spin-out from a university with very scientific and academic founders. And in our case, we have 4 founders, and all of them have a quantum computing background. I was doing a postdoc at Atos University in Finland, working there in the group of Mikko Möttinen, and he's still working as a professor at the university. So being a founder, he keeps the university group alive. And our CTO, Juan, I met him in Finland, but then he went on to Sydney, and then we were very lucky actually to get him back. And in this way, the idea really came from this, let's say, technical motivation to build a quantum computer at large scale. And back then, this was done mostly in the universities. And what we have been seeing over the years is that the technology is kind of escaping the university, the academic field, getting into industry. And so the motivation is that it's such a complex topic, and it's about system scaling, system engineering. And this is usually nothing that is a task for universities. Universities are great to discover new groundbreaking technologies and maybe also develop individual components to the kind of maximum of performance levels. But then when it comes to building a complete system out of it, this is usually done in industry. This was the idea that we said, okay, what really drives us is this fundamental task of building a quantum computer. We thought that the best way to do it is in a company. And so we decided then around end of 2018 to spin out a company to address exactly this need, because even with the best algorithms, you cannot do a lot if you don't have a computer to run them on. So someone needs to build the systems. And of course, we have back then already seen a few of such developments, especially in the US. And this also kind of gave us a little bit this ambition to build here really a company that, of course, has the roots in Europe, but then that can compete on a global scale. And this is kind of the ambition that we have, that we say, okay, we have actually all it takes in Europe. We have the technology, we have the great people. So let's just do it and build out a company which is there really for the long run and that can compete globally.
Great. And now, so 3 or 4 years later, you have a company, a big company that competes globally and have involved in international projects, and you have multiple offices also in Europe, in Spain, in Germany, in Finland, and also since the end of the last year in Paris. Can you explain a bit what is your strategy for quantum computing in Europe and specifically for France, for example?
Yeah, sure. And actually, I'm currently sitting in our Paris office, so speaking from France here today. And we think that quantum computing is a very challenging task. And anyways, you cannot do it alone as a single company. So you need an ecosystem, and you need the best people. And we live in a world where, because of technologies like, for example, video calls, actually you can work in a very distributed way also with your team. So one of the ideas of a little bit going in different places and in Europe and establishing offices is to get access to the best talent that is out there. And obviously Paris has a very strong academic ecosystem. So there are great universities, and of course, as a result of this, there are also great people on the technology side here in Paris. So this is one thing. And then, of course, we also want to make business. And so our business model currently is to sell the complete quantum computing systems, and the target customers are supercomputing centers. And also in France, actually, you have a strong ecosystem for supercomputing centers, one actually being also located here in the south of Paris. And the way we address this market, again, is we don't want to do this alone, but there we also are following a partnership strategy. And of course, today also here in this Fireside Chat with Eric being here, we have a very strong partnership with Atos, and we want to strengthen this also in the future. And we think that sometimes it helps actually if people are close by and can meet in real life as well. So this is another topic, of course, for us, this kind of HPC integration, driving this forward as well with very strong partners here locally.
And can you tell also a bit about your German projects? I think you already mentioned them in your presentation in the morning. Maybe you can elaborate a little bit what's going on now in Germany regarding your collaborations and projects here.
Yeah, it's a similar thing. Also in Germany, you have similar strengths as the ones that I just mentioned. And we settled in Munich, and in Munich also you have a strong supercomputing center in Garching. And these supercomputing centers, their kind of business model, if you wish, is to own computers and distribute the computing time either to scientific communities or industrial customers or so. And in this sense, they really have a need for the hardware. They want to be able to operate the hardware, get the best performance out of it. And of course, if you have a new technology like quantum, first you have to get used to it. You have to know what does it mean to operate a quantum computer, how do you integrate it, at what level. And we have a project in Munich where we are developing exactly answers to these questions. And also we are delivering then a complete system there to the supercomputing center. And again, in a partnership model. So we are not doing this alone. Atos actually is part of the project as well. And then we also have a software company, HQS Quantum Simulations, which delivers part of this scientific computing stack. And in this way, I think we really create there a situation in a, let's say, open innovation project where a local installation of hardware then hopefully helps building the local ecosystem. This is something, for example, that we have seen in Finland, where we have already delivered the quantum computer. And we are now seeing that software startups, for example, are going to Finland or are being founded in Finland because of the availability of hardware. So we really think that these kind of local projects, they have a very strong impact on the whole quantum computing ecosystem.
You mentioned availability of the hardware, and I would like to go to the topic that actually been mentioned for several speakers today already, is the supply chain of quantum computer. Can you maybe tell a bit in detail how does it look? What does it include? Which components does it include?
Yeah. I mean, in a sense, a quantum computer is a computer. So it has similar components to a classical system. So you have a frame, you have a processor, you have some electronics and these things. And of course, for the quantum computer, it depends a little bit on the base technology that you use. We are using the superconducting technology where you actually produce chipsets, but there are also other technologies out there based on, for example, trapped ions or so, where you have slightly different components, for example, lasers instead of microwave. But I think the concept is always the same. You have some kind of a processor. And in our case, as I said, it's a superconducting chipset. So we are starting with a silicon wafer. And this is something that we do in IQM. We design the processor layout. We simulate the performance of the processor. And then we tape it out and package it. But then kind of this is the key component that we bring in. But then on the supply chain side, for example, you need the electronics and you need amplifiers. In our case, you also need some cryogenics. And this is, of course, something where, for example, in Europe, I think we have a very strong standing because we are in a lucky situation where we can build a complete system where I think most of the components actually come from Europe. And talking about kind of competitiveness on a global scale, I think this is also very important from a strategic point of view.
And what parts of the supply chain do you address as an IQM?
Well, as I said, so we built the processor ourselves, and then we assemble it in a complete system. And most of the pieces of the system we don't produce ourselves, but we get them as third party. And then we of course, we deliver to the customers. But the computer, of course, also contains the whole software stack. And there, actually, we don't develop the complete software stack ourselves. We develop the low-level software, let's say the firmware, if you wish. And then we interface with the most common programming languages. So, for example, again, talking about Atos, you can use the QLM interface from them to connect to our systems and then make it a system that can be accessed from an end-user perspective.
Mm-hmm. Thank you very much. And you mentioned that the supply, so the quantum computer supply chain, at least in the, if we're speaking about superconducting quantum computers, are very much developed already in Europe. Do you see any particular weak points that should be addressed early on, or possible vulnerabilities?
I mean, of course, you can think about which components do we not produce here locally, and this is very much the classical high-frequency electronics that you need, for example, FPGA cards, this kind of electronics, which is usually not coming from European vendors. They are, of course, I mean, it's not a problem per se, as long as we are sure that also in the future we are getting these components. And now in times of a chip shortage globally, of course, this can be a problem. If let's say someone tells us for this FPGA board or so, you have a 2 years lead time, and we need to deliver a system to the customers in 8 months or so, right? So this is something we have to manage, and we have to make sure that either then we buy in stock, and of course there, also being a startup, maybe you don't have the same negotiation power as a very large customer, and this is something that we have to address, of course, to make sure that we can deliver also the projects that we need to bring to our customers.
Thank you very much. Can you maybe also elaborate how does IQM quantum computers look on the in a competitor environment? What makes what you offer is different from other offers? Mm-hmm.
So, of course, I mean, one thing is the technology base, and you can start arguing which technology is better, ion traps, cold atoms, or superconducting. But I don't want to go into this topic. I think this is a complete session as such. But if you think about more kind of what do the customers need and what do they need now and maybe in the future, we are very much focusing on finding solutions that add values to customers already now. And I think this is something that many people think, okay, it has to be the industry from the start. And I think this is a little bit the stretch that we are seeing in the field. There are many big claims being made about quantum advantage when the industry will use it. But we think actually there's a lot of value already in the years before, basically in the phase where we currently are, where customers are maybe more on the public side, more on the scientific side, where they want to get ready. And there it's really about being able to deliver, being able to build them a system that they can use for their purposes. And there are actually not so many. If you look at the landscape of companies out there who are actually able to deliver a complete system to on-premise to a customer. So this is, I think, one key point. But then, of course, if you look at the technology, something based now going a little bit into the technical side of things, on the superconducting side, one of the advantages is that you design these processors. So it's very much an engineering task similar to classical processors, and you have a lot of engineering degrees of freedom. And this is something that we use actively. So we design processor layouts for specific tasks. And the idea is that these processors, they are much more hardware efficient. So let's say in a simplified way, you could say you need less qubits or less gates to run the same algorithm as with a general purpose system. And we have, for example, a recent publication about an algorithm in NMR imaging, so coming from the life science side, where based on a specific processor topology that we have developed, you can reduce the number of gates by a factor of 10. So it's really a significant improvement when you use a specialized processor architecture compared to a general purpose that maybe others are using.
Thank you very much, Jan. I would now like to invite my second guest, and we'll see you again, Jan, at the end of the discussion when we will have a conversation with both of you. But now I would like to invite here Eric Eppe from Atos. He's a global head for solutions and portfolio for HPC, AI, and quantum. Welcome, Eric. Nice to have you here. Thanks for joining me.
Good afternoon. Thank you for inviting me in this call. Thank you.
My first question, can you please tell a bit how and why quantum computing became a part of the strategy of Atos company?
It's a long story, but to make it short, we are developing HPC supercomputers for now 15 years, and we became very humble at the beginning with what we've done, because it was not a lot of people developing a supercomputer at that time. And now we are at the moment where we are #1 in Europe and #2 worldwide in the supercomputer business, so in the high end. And effectively, we were always looking at ways to implement combination portfolio to make the supercomputing much faster than it is today. So we are, as everybody in this business, eating the Moore's law, and effectively, if you want to build coming from a teraflopic system to petaflopic system, and now we're discussing exascale system in the future, let's say in 23. Well, it's a good business because you're making a bigger system, but effectively you're consuming a lot of power, and you're not effectively solving the problems that you're trying to solve. So because the efficiency of these systems are not very, very high. So the question was raised years ago, and how do you solve this problem? You scale the system by adding more hardware, but you're not effectively delivering a faster solution to the customer. So you scale, but not at the same level as the hardware is scaling. So we found several ways to do this, to solve this problem, and one was including AI into the simulation. I mean, building some AIs to reduce the number of parameters to some equations, and this is one way of doing things. So effectively, you're reducing the size of the problem, so you can get faster to the solution. And that's one way, and we do it already. So we are doing what we call hybrid simulation, using traditional scalar systems, or even using GPUs. And we use AI in some part of the workflow to accelerate the workflow. So this is one way of doing things. And so we had the same sort of thinking, I would say 5-6 years ago, and say, okay, what will be next? Because AI, okay, we are starting now. It was in 15, 16, and we started to have this discussion, and we are aiming in that direction to do hybrid supercomputing. But what's next? And what's next is obviously quantum computing, because the promise, and even if Jan said that we need to stay calm about the promises of the quantum leap. We don't know when it will happen and how it will happen, but I think that there are different solutions to accelerate the simulation. Quantum computing has some promises, and even if you don't reach a very high number of qubits, with a specific number of qubits and stables and a good quality qubits, you can solve some part of the workflows much faster than you would do with scalar computing or even AI. And that's what Jan was referring to, co-developments of specifically some, I would say, QPUs, I mean, quantum computing hardware that is specific to solve one sort of problem. And we think this is really a good idea because if you succeed in being, let's say, 100 times faster on a small part of an algorithm, accelerate that part of the algorithm, you can scale much faster in the overall workflow. And this is really what we are aiming at. This is about hybrid computing. Now, what we did in 16, we decided to go into the quantum computing, but we didn't want to go after real hardware first, because we thought that it was too early to do that. And as Jan said, there's many fields, and we are not going to comment all the different ways of doing quantum computing today. But we thought that the best way to do it was to start to simulate a real quantum computer. And we have some specific type of server with very high memory size, and with that we can simulate up to 41 qubits, real qubits, in our machine, which is maybe not as large as everyone would think, but this is enough to simulate real problems with real circuits. We have a programming language called Quasm, and it's based on a Quasm, and we can simulate many types of different QPU technologies, including the one that IQM is doing today. So this is very interesting because this is another way to say to our customers, well, you don't know which technology will be first on the market, which technology will break everything. You don't need to choose now, but you need to start now, because you need to start to program with your, start to do some POCs, start to do some use case with quantum computing, translate your use case that you do today with traditional simulation into quantum computing, because when it will start and when real hardware will be available in quantity and at large scale, if you're not ready, you will be passed by many other competitors who had worked on it already. So this is the same, our market analysis today say that it's the same mechanism on the market that some people, some companies in the US and others or in other countries used with AI. They started with AI very early, and now they have such big market footprint that no one else on the market could just stay on the market, right? And there are many examples in the US, many examples in China and elsewhere, that the first mover advantage is so big that nobody can follow. And so we think that the people who will be first on the market with real hardware and who have understand really how to implement hardware linked to real application to solve some very specific problem will gain advantage on the market, or will give advantage to their customers. So I think, for instance, what IQM is doing with their QPU today is really very smart, because they are trying to solve some very specific problems. So they are making I would say a general QPU on the market, but they have also a strategy to solve some very specific problems with some specific QPUs. So this is smart, and we completely follow this route to the market with them.
Thank you very much. And can you elaborate a little bit more on a simulator, on quantum simulator? How does it compare to a few other quantum computing simulation tools on the market?
So the main difference, I think, with traditional, there are several, let's say, linear algebra simulators on the market that are freely available. We do that. I mean, we have a linear simulator. That was the first simulator we had, but we also have we can do also noisy simulation. We can mimic with our tool set. We can mimic any technology, and that's really. I don't know if we should say simulator. I think we should say emulator. It's better suited, because we can emulate any hardware, and even the stability and the noisy part of some hardware. And this is really what's important here, because the size of the number of qubits is one thing, but being able to simulate what the hardware will be, or to emulate what the hardware will be in the future is key. So we can do both circuit-based, but also analog-based simulation. We are also adding simulated quantum annealing simulator, which is very powerful, actually, with 20,000 spin available, which is very big on the market. And so you have all these tool sets that you can not only use separately, but you can use them jointly in your program, which is quite unique on the market, because usually on the market you may find one or the other. You can program them one way or another, but you have difficulties to combine them together, and we can do that.
Thank you very much. I would like to go back to the topic of quantum computing as a technology that will advance innovation in high-performance computing centers. You already mentioned shortly about the main driving forces and then the innovation, the pressure to innovate. Can you please tell other technologies apart from quantum computing that can bring maybe similar effect, and what is an advantage of quantum computing in comparison?
Well, this is a big question. As I said today, in simulation, because this is really our market, right? At Atos, what I'm driving is this market, and I think to answer your question, I think this is we cannot say that one technology is better than another. Obviously, quantum computing has a lot of promises, and we really hope that at some point of time it will boost really the simulation and the time to solution, and the depth of that we will be able to simulate. But we really think at Atos that the future of supercomputing is not monolithic. It will be a mix of many different technologies, hardware technologies, software technologies, and we trust a lot about software technologies on top of our hardware. So what we are doing today, and what we'll do in the next 5 years, is using all the different hardware available could be traditional CPU. There is a big trend towards GPU. And 3 years ago, nobody wanted to use GPU. Now everybody wants to use GPU, even to simulate quantum computing. We start seeing some FPGAs popping up into some part of the simulation workflow. And we are integrating AI, as I said before, and we will be integrating quantum computing hardware into our supercomputers when available, when we have the chance to make it happen, and we're sure it will happen. So it's a mix of different technology that will make us more powerful in the future, that makes these supercomputers more efficient. What we're trying to do is to make the whole thing more efficient. If you think, just to give you a side note on that, what's really at stake here is how you make this thing very efficient, much more efficient than what you have today. If you think of a petaflopic system today, it is usually agreed in the industry that the average application efficiency is about 18% of the peak performance. So, well, if it's petaflopic, let's say 100 petaflop system consumes, okay, let's say 5 megawatts. 18% of the 5 megawatts are really used to deliver some results, effective results. This is a really poor efficiency. So everything you do to increase this efficiency by using accelerators like AI, with by nature preparing to solve some problems much faster than simulating brute force like we do today, or using quantum computing, which will solve problems in a much smaller and much lower number of cycles, I would say. You will be increasing the efficiency of these supercomputers to increase the number of flops per watt effectively. I just wrote what the previous person, Mr. Berger, said about the brain power, 100 teraflops consuming in 20 watts. Well, this is very efficient. If we had this sort of efficiency in a supercomputer, it would be very interesting, right? An exascale supercomputer is going to consume between actually 20 and 50 megawatts today. The US frontier system is consuming 53 megawatts. In Europe, we are aiming at 20 megawatts, but it's still not very efficient. So every acceleration will increase the efficiency, and this is what we are trying to do.
And where do you see the main, what are the main requirements for integration of quantum computing into high-performance computing centers from your point of view? Requirements and obstacles, if you see any.
So the main requirements are today there's a lot of unknowns today, right? Doing hybrid computing with quantum computers is we don't know exactly how the workflow will. There is software ecosystem that needs to be built, right? Because some quantum computers have their software stacks, some don't. There is a paradigm today that is widely used in the supercomputer industry, which is MPI or OpenACC, or I mean there are different paradigms to develop applications, and they are very much different to today to what is being done with quantum computers. It depends on the technology that are used, but so there is a sort of ongoing discussion, and there will be some probably some work being done widely between Europe and countries and US and there are many players here who are going to push for standardization on this framework, the programmation framework. And so we are working on that. There is a big program in France actually called HPCQS, in which we are involved, and we are not alone on this, to go in that direction and develop this type of framework. That's, I think, the main inhibitor for the moment. I think the technology will evolve on the hardware side, and also there is a different a second domain, I think, which is important, is the way to program and the way to interact with a QPU today is much different from what we are used in the simulation, parallel simulation today. So it's very much different. And there are fields that will probably need some, I don't know, changes in the way we program things today. For instance, way to improve the efficiency and the interaction with the quantum computers called VQE, Variational Quantum Eigensolver. And this is very interesting, and maybe Jan can interact with me on this. But it's very different from what's being done in the traditional simulation, and it's very powerful, but it's very different. So the programming paradigm is going to be different. I think also the people who are programming today are used to program in traditional programming languages like Fortran or C or even C++. Well, it's not probably the same people who are going to program the quantum computer. So that's probably another problem in the industry.
Thank you very much. I would now like to invite Jan back to our improvised room with the fireplace. And I want to ask you both a question. In your opinion, what type of HPC centers by focus area will be probably the first one to adopt quantum computing?
Jan, you want to answer?
Sure, I can start. I think, when we talk about early adoption, I think it will be mainly the more scientific computing centers, because they are very much interested in kind of finding out new ways to compute new solutions. I think a lot of innovation in the field of high performance computing is happening in these more scientific supercomputing centers. And then once it's proven that it works, that it's kind of production ready, then we are ready to go also to more industrial ones. So just to give you an idea, if we talk about quantum computers and compare the uptime of the current systems, which may be the requirements that the industry has, we are not there. I don't know the numbers. I guess Eric knows better the requirements, but I know that our computers need to be calibrated once in a while. And so they are not kind of 24/7 online. And I think these are challenges we have to solve together somehow.
Yeah, so uptime is, when we sell a supercomputer, the uptime is usually above 90%. So this is really, so a supercomputer is a production system today, right? It's really a real machine going in production, solving big problems. I used to say, and I think Jan, please interrupt me, but I used to say when I meet customers that, okay, double quotes, it's a QPU is experimental today. It's a product, but still experimental in the way you don't get the same level of uptime, and you have to adjust, you have to learn, you have to, it's a very different paradigm. You have to learn a lot. It's a different thing. It's a different animal. So, well, and related to your question, which center? There is a lot of academic centers in Europe who are interested to that. Not only in Europe, there is a big tender coming up within the Euro HPC program, and there is an RFI asking for hosting entities. So sites who will be willing to host a real hardware, real quantum computer. And so this is going, I think, end of June. And after that, so next year, there will be maybe around 4 centers in Europe with QPU. LRZ, on which we are both involved in Germany, is going to host 1 QPU from IQM. When is that, John? 23, 24?
Yeah, so we're now starting with the preparations. I mean, again, it's a learning curve, right? So we have to discuss together with the supercomputing center about the requirements, let's say from vibrations, all of these topics, cooling water, and they are now getting the room ready. And we are then, I think in 2023, are having the system there, yes.
And then, yes, so today we have our biggest customers are very large centers, tier 1 or tier 0 customers in the world. But we also have some commercial customers. And when I say commercial, I mean companies who are very are requiring very big systems to do some special things. So you should think of weather forecast, for instance. They really need to have a big supercomputers. But in the oil and gas industry, for instance, there is a lot of needs for very big machines too. And then you have other types of customers who already need some big machines. So obviously, academic centers are the first customers for quantum computers, but you might think that some of these big other customers will also require something in the future if there is a significant leap or significant gap, I would say, of increasing or decreasing the time to solution. I think there will be some customers in the commercial field quite soon.
Thank you very much. Jan, I have a question to you. I think you already probably spoke to that point shortly. Is there any, how does superconducting computing technology compares to other modalities in regards to integration with HPC? Is there certain advantages in this area that superconducting technology offers?
I mean, one of the strengths of superconducting technology is that the gate operations that we use to implement the algorithms, they are rather short compared to other technologies. So usually, let's say a gate, 2-qubit gate, or also a single qubit gate, you can do it in a few nanoseconds. And if you kind of calculate a clock cycle from it, you get into the megahertz regime or something like this. And this is very similar to kind of the frequency of classical computers. And I think this is important when you think about maybe not the first steps in HPC integration, but we see it more like the whole HPC integration topic is kind of a roadmap. Maybe we start with just kind of connecting two systems through a fiber or a network cable, but maybe in the future you also want to have a more closer connection really on the hardware level, and you want to have low latency and fast feedback. And then of course time matters, and then it's super important that you have fast reaction times, fast gates, so that these two systems can really work in sync together. And I think this is one of the big strengths that you have with the superconducting technology, that you can actually operate very, very fast gates and then in real time also pass feedback back into the system. So for example, if you think about error correction, basically there you need to kind of detect the errors and correct the errors more or less in real time. And of course, there you need a lot of classical computing power in the background, and you need to have the ability to have a fast communication of a lot of data between the classical and the quantum system. And I think this is one of the strengths of superconducting technology, that they really fit nicely into these requirements.
Thank you very much. Now I have a question to both of you. Would be interested to know about your perspective between the cloud access for quantum computing versus on-premises access. What is your opinion? What is the dynamics there? You can start, maybe Eric.
Actually, this is a very good question. So. Well, I think it depends on the. So, okay, let me think a bit. So I think there are not everybody is in real need to access a QPU today. So I think it's really for people, scientists or customers who have a real need to experiment. At very high level, their algorithms, and they really need to understand how they work on a real hardware. But everything you do on the real hardware today, you can simulate on a QLM. And so what I think is the trend is obviously for cloud computing as an access to run some specific circuit, and then to run some specific QPU. So if you have let's say a community of people who are experimenting or developing, or I would say inventing things around quantum computing, and they want to test their stuff, their programs on a quantum computer, they can go cloud, and they can access some QPU through the cloud. And cloud could be a QLM connected to from our way to an IQM QPU, for instance. But if you go beyond that, if you want to do hybrid computing, so it's a different story. So cloud is just a matter of accessing the whole system being a supercomputer with some accelerators like quantum computing QPU. But just to summarize, I think there is need for cloud for people who are just experimenting, and not, I would say, for real production systems. Production system will go either on-prem to our customer sites and being accessed through a cloud, or just being used as they are traditionally used on premises.
Thank you very much. Jan?
Well, I very much agree to this. I think there will be anyways a coexistence of both, and we will have a need for both. And the question is, what is the ratio, of course, and what are in the end the benefits? And I think at the moment, it is important to have the systems in the cloud, because people need to develop also the algorithms and test and do the proof of concepts. And obviously with the cloud, you can reach a kind of a very broad user base. It's also about making maybe then the technology available to people or organizations who maybe don't have the resources to get a quantum computer, right? So we want to kind of really benefit from the know-how everywhere in the world. And of course, the cloud is something that helps there a lot. But as said, on the other hand, we also need the hardware. And I think especially in the early days, it will be a lot about performance. So how much can we squeeze out of the processor, because we are limited by the hardware. So we need to make sure that we use the hardware in the most efficient way. And usually these kind of performance topics, those you don't really get in the cloud. So there's more like a standardized system that you can use and maybe access. But when it comes to really get the last performance percentage out of the system, I think you have to have an on-premise installation.
Thank you very much. We have a little bit time left. I have one last question for you both. If you can just make a short, maybe a summary or a statement, what would be the first step for HPC centers to start exploring the potential of quantum computers? Where should they start? Jan, you can go first.
I mean, usually, again, of course, it depends on what kind of a center we are talking about, but these more scientifically driven centers, they address a lot of questions which are related to physics or quantum. So they have already some kind of know-how about quantum physics, at least in many of the cases. And there, of course, they have some exposure to it. But of course, it's important to think from the kind of user perspective and think about, okay, how can a quantum computer accelerate my specific problem that I have? And of course, there's literature out there, you have your own people. And I think then you can also play around. This is what I kind of mentioned with making the systems available through the cloud. If you just want to figure out yourself, how does it work? How does it feel, so to say, to program a quantum computer? I think these cloud offerings are very important. And so, for example, we conducted also together with Atos and IDC a market study. There, I think for me, this was quite interesting that actually the numbers, if you look at the results, there was that in 2023, actually, the majority of the centers, they will explore quantum through the cloud. And I think the reason is that also they, of course, they need to get ready, they need to get their budgets ready as well. But then if you look at the 2026 number, already the majority was thinking that they would have an on-premise installation. And I think this is a little bit what we see. It's kind of getting quantum ready, for example, through testing out cloud services. And then once you're convinced that you really benefit from the technology, then make maybe a larger investment in an on-premise installation.
Thank you.
I fully agree with what Jan said. So I think the academic side is covered. I think we started seeing in 21 some customer cases popping up. When I say customer, I don't mean academic side, but real customers with real problems, and they're trying to think what is the what sort of problem I can solve with quantum computing in the future. Not now, because they know it's not possible really now, but they start working on that. And so my perspective and our perspective today, beside the academic side, because we're also looking at that closely, but I think in the future, quantum computing will solve problems. And besides I would say the traditional academic, very research-oriented topics that are really good because they are the base of the problem you have to solve. We need to think of the what sort of problem we will be solving for the customers, and this is really key today. We have some ideas. I mean, Jan and his team has a lot of ideas too, and many people in the field have ideas about what will be the first problem we can solve with a quantum computer, and we need to think of that and address that for our customers, our future customers, and help them start. Okay, and so with the Atos QLM and with the help of IQM, we have a complete tool set to make that happen. But it's not as important as understanding what the customer are going to do with that, and help them doing it as fast as possible, and not just being I would say focused on the number of qubits and the size of the thing. I don't think the size is important here, and I think Jan would agree with me. The size is important. It will be important in the future, but what's more important is what sort of problem you can solve with the available small side for the moment, available hardware. I think there's many things we can solve. We just need to be a bit smart and understand the customer problems and what sort of problems we can solve for them. And this is what we are doing, by the way. We're trying at least.
Well, thank you very much. I think it was a nice conclusion for this conversation. I think we learned today a lot about the integration between the two worlds of quantum and high-performance computing. I thank you very much for joining me in this discussion. And
thank you very much.
Thank you.
Thank you.
Our pleasure. Bye-bye.
Bye.
So, dear participants, that was it for the first day of our Quantum Summit. And now it came to the conclusion. And you, of course, you're very welcome to stay online on the platform and keep networking with each other and connecting with each other. And the recordings of today's sessions will be available starting from tomorrow on the event platform. And tomorrow we are starting at 10 o'clock and we will have more talks and discussions on 2 parallel stages. We have a full day program and we will discuss more how can industry start exploring the potential of quantum computing, what are the entry points, what are the starting technologies, what are the available use cases that already known today. So come back tomorrow and at 10 o'clock and make sure to take a look at our program. And I would like to thank at this point our partners and the speakers of today, and of course you, our audience and participants. And I would like to wish you good evening and see you tomorrow.